Hey Wayne, how you doing?
Good. How are you?
Good, good. How's the studying coming along?
It's coming. It's coming. I I just a second here. I think just like our my fellow students, it's a balance. Just trying to get that balance between work, family, and getting these questions answered and remembering the topics actually.
Sure. Yeah, it's definitely a lot to juggle. Is this your first time taking the exam?
No, so I've taken it twice before. The first one was self-study. I thought I'd check it out, see what it's all about because taking the FE, I self-studied and I passed on the first try. So try to roll the dice. And the second time I signed up for another course. I won't name names. But I
Name and shame. No, I'm just kidding.
yeah, but it's going through that process, it just felt like reading from slides and this is the information, just take it. So this is a very welcomed contrast now doing your course, I must say.
Great. Great. When is your exam date?
Scheduled for April 22nd.
April 22nd. Man, I want to say the study session I was in yesterday with Michael, I think he's also scheduled for the same date. I think he mentioned April 22nd.
I saw that. I watched that. And yeah, so
Good,
I
good.
guess we'll have it on the same date.
So let's see. So this is going to be your third attempt, first attempt with our program. I get a lot of emails all the time where people are asking like, "Hey, what's the secret? What's the secret sauce?"
Yeah,
And there, of course, there's no secrets, but I always recommend if you've taken the exam before, even if you self-studied or if you took a different class, really check these strategies we talk about during class one and really make sure that you're kind of in alignment with those study strategies, study schedules, test taking strategies, all that good stuff. Because even if it's your first time with our program, if you've already taken the exam before, you always want to look for, man, what are the things that had I done differently may or may not make the difference. So that's definitely a big, big recommendation for you.
yeah, yeah. I definitely making changes based on the recommendations, and I've seen improvements. Just how I tackle problems. It takes the nerves out of it. Just doing more problems, and as
Yeah.
before, I would just go through lectures. Oh, I got this, and then when it's time to really dig into the problems, then scrambling to remember stuff, and that takes it out when I practice more.
Yeah, it's definitely more of a challenge doing it on your own, right?
Yes, absolutely. Yep.
Another big thing I recommend, and it's kind of why we structure the homework and the qualitative problems for after class, but then the pre-work before classes. Anytime you learn something new, yeah, it's easy to follow along, right? When someone that's explained it for years, it's easy to follow along and it makes sense. But it's a lot more challenging when you're by yourself trying to arrive at the right answer without, any help. It's always going to be a benefit to try to work problems right away once you learn something new, so that the material's still fresh. You're still gonna have to go through the thought process like, man, fork in the road. Do I go this way? Do I go this way? Is this a red herring? How do I solve for this? But the sooner you can go through that experience for a new subject after learning it is the best. It's the quickest way to kind of move all that information from like short term to long term working memory.
Completely agree. Yeah, I've seen the difference.
Yeah, so what else? Have you been able to do 1 hour, a 1 8-hour session once a week?
Yeah, I try to allocate that to Saturdays and squeeze in a couple hours on Sundays. So that's been helpful. That's one of the main contrasts between now and before.
Excellent. Yeah, it's certainly not fun, especially the first
Yeah,
couple of 8-hour sessions you do, but that's the whole point. That way, when you take the P exam, you're used to that long mental marathon, that long pace.
yeah.
So that's good to hear. Have you been able to keep an index of all of the problems that you're getting wrong or guessing on?
Yeah, I've started that just recently, just a couple weeks ago. But I'm building up that index. Again, it's a challenge with, you know, going through the study sessions and then taking that time to work through problems and logging. But yeah, I've started that and I'm increasing it.
Great, good, good. Yeah, you can almost think of that as, your personal practice exam, right? I always like to say that that represents the current problems that are challenging you the most. Everyone has their own strengths and weaknesses. For some, it's motors, for some, it's protection, for some, it's just circuit analysis. But you never really know what your areas are until you actually log them. And it's like, oh, wow, I've got 12 circuit analysis problems here that I've gotten wrong from various sources. Only, two motor problems. Like, I need to spend more time in circuit analysis now. So that's good to hear. And what else? How are you liking class so far? The pace and the engagement and all that good stuff?
Loving it. It's, helpful to at least, if I have some free time, just going on the forum, just checking questions and responding here and there. That has proved very helpful to me. Because again, with work, there are gaps in between the last class and the next class, and then when I had time to do the homework. So those little nuggets in between where I see questions pop up on my phone and I read through it, I think it's helpful. It's a little mini refresher when
Good. Yeah,
when you have
helps to keep it fresh, right? Helps to keep those plates kind of spinning and the
yeah,
wheels turning.
exactly.
Awesome. All right. Well, were you able to print out that PDF I sent you? Yes, sir.
Yep, I have it right here.
Great. So we'll go for the next hour. I've got that pulled up here on my screen. Same disclaimer I always like to give at the start of these study sessions. You're in the driver's seat. So my goal is always to get as many done as possible for you and to
Uh-huh.
cover as much as possible. But if you feel like if you feel like you want to skip ahead, anything like that, feel free at any time to say, "Hey, I'm good here. Let's move on." Or if you want to kind of keep going on a particular subject as well, you're in control. The whole goal is to get as much information across as possible in this next hour.
Okay.
All right, so let's see. First one we got queued up was the reliability problem from the technical study guide, problem 19. I will say that next week when we do applications, we're gonna have a lot of really good examples on reliability. So after next week, I don't think this problem will give you any trouble at all, but we'll definitely still go through it and I'll give you kind of the crash course on the reliability block diagram that we'll talk about during next week's class.
Okay.
So when you're working reliability, especially with regards to an electrical system, you always got to read the problem. The first thing I'm looking for, if they're asking me to calculate the probability of, like, say, reliable electric power, just like this problem is saying down here for this customer bus, my first question is, okay, my generators are connected in parallel, my transformers are connected in series. But is each generator big enough to provide power to the customer? Are they redundant? You'll see next week, I'm going to get a lot of people with that during class, but depending on how large the generator is to the customer load, it can change how we model the reliability block diagram. So that's the first thing I'm looking for, right? I know it's asking me for what's the probability of reliable electric power for the customer. And then next, I'm looking for clues to tell me when I model my block diagram, my reliability block diagram, am I going to model it exactly how the equipment is connected? Or am I maybe not, depending if these generators aren't big enough? For example, if I needed both generators to provide power to the load, then they're not redundant. And in my block diagram, they'd have to be series instead of parallel. So then, boom, right here in the problem, it tells us assume that the generators are redundant and each has enough capacity to provide power to the customer bus shown below. Meaning, even if generator number one fails and is unreliable, generator two, big enough for customer, and vice versa, generator number two fails if it's unreliable. We know that generator number one is large enough for the customer. You with me so far?
Makes sense. Yeah.
Excellent. So then the next thing I'm going to do, we've got the probability of reliability for both generators and both transformers. The reference handbook calls this variable P. Some other books will call it R for reliability. Generally, I like to use R because P, we use it all the time for real power in watts. So, but you'll see the reference handbook formula calls this P for probability of reliability. And then this next variable here, probability of unreliability. Typically, we use F for this for the probability of failure. Um, One important formula that's not in the reference handbook is if you sum up reliability with failure for the same asset, you'll always get one or 100%. So the probability of reliability for generator number one, 0.92, that's R or P. Probability of unreliability for the same generator number one, that's 0.08. That's the probability of unreliability, also known as probability of failure. Again, you add up 0.92 with 0.08, we get one. And that's going to come in handy when we sum these up. All right, so the next thing is I'm going to draw out what's called a reliability block diagram. And for this particular problem, it's going to look just like the single line diagram. That's not always the case, but again, since both generators are redundant, we only need one to provide power to the customer. That lets me model generator number one and number two as parallel. Not electrically parallel like in the single line diagram, but parallel from a redundancy standpoint in reliability. Does that make sense?
Yes, it does.
Awesome. So here's my first, here's my first square or block rather. Here's the second block. And then we got both of our transformers. Maybe scoot these over here. All right, so we've got generator one and generator two. This is my reliability block diagram. They're in parallel, meaning, again, generator number one is big enough by itself. Generator number two is big enough by itself to provide power to the customer. So the path can take either direction in this block diagram. And then transformer T1 and transformer T2, we've modeled their probabilities in series, right? Because if I lose T1, doesn't matter what the generators are doing, customers in the dark, right? Same thing if I lose T2, doesn't matter what this transformer or both generators are doing, it's a series transformer, we know the customer's in the dark. So that's why we're modeling transformers one and two in series in our block diagram. All right. The reference handbook provides two formulas for adding either series blocks or parallel blocks, and I've got those on the next page. I'm assuming you've already read through that solution the first time you work this problem.
Yeah.
So I'm going to show you a quicker way to solve this that's not in the solution. And again, it's one of the things we'll be talking about next week on class 10 applications. So the easiest, we'll start with adding series blocks. We just multiply the probability of reliability. So for transformer T1 and T2, here's their reliability probabilities. So I can simplify this block diagram into a single block for both transformers. So this would be transformer T1 and T2, the equivalent series block. And all we do is we're just multiplying these two together. So probability of reliability for transformer one is 0.96 times the probability of reliability for transformer number two is 0.94. That means, again, combined, when we combine these into their equivalent single block, this single block has a probability of 0.9024 or about 90%. Are you with me so far?
Yes, I am.
Excellent. When we combine parallel blocks, instead of multiplying the probability of reliability, We actually multiply the probability of unreliability, or we multiply the probability of failure. So for generator number one and generator number two, I can find the equivalent probability of unreliability by multiplying these two values together. So let's see, this is a probability value. We can call it P or R. Now we're going to calculate the new equivalent probability of unreliability for just the generator. So that's going to look like this. Here's our transformer. And this is like G1 in parallel with G2. So their probability of unreliability, we're going to multiply 0.08 times 0.13. That gives us, again, not a probability of reliability, but it gives us a probability of failure or a probability of unreliability for both generators. Comes out to 0.0104. Are you with me so far?
Yes.
Great. So now I got two series blocks, right? Before, when I had two series blocks, I could combine them into their equivalent single block by multiplying by their reliability probabilities. So now I've got two blocks in series again, but I don't know both of their probability values. I know the probability for transformers one and two, but I know the unreliability probability for generators number one and number two. So before we can multiply these two together to simplify them, like we did previously, we just have to convert this value from a probability of unreliability to probability of reliability. Then once I have this P value or this R value instead of F, then I multiply them together and we're done. So to convert between reliability and unreliability, again, we got to use this formula that's not in the reference handbook that says for the same asset, for the same machine, for the same system, R or P plus F will always equal to 1. So I know the F value of the combined parallel generator one and generator number two, right? That's the last value we calculated. So to calculate R, I can say R equals 1 minus F. This is just called taking the complement. We're just taking 1 minus F gives us R. You can do the same thing for F. You can say F equals 1 minus R. You're just solving for the other variable. So in my calculator, that last number, I'm just going to say, hey, calculator, what's the complement of F? What's 1 minus that last number you gave me? So that comes out to 0.9896. Again, you can call this R or you can call it P, as long as we realize it's just the reliability probability. All right, so now what do? We're back to, we got two series blocks in parallel, or excuse me, two series blocks, not parallel. We know both of their reliability probability values. How do we convert this to one last final series?
Gotta multiply them together.
Yeah, multiply them together. So this is like, we can call this G1 in parallel with G2 plus T1 plus T2. That's this final equivalent block, which essentially it's going to give us the overall reliability of the system, which is reliable electric power to the customer bus, assuming both G1 and G2 are big enough on their own that they're redundant. So my calculator, 0.9896, that's our reliability for generators one and two in parallel. So I'm going to go back to my calculator. I'm going to multiply this by, and I'm scrolling up and I'm finding the previous equivalent for T1 and T2. And all we're doing is we're multiplying this probability value with this probability value. I've got it labeled P over here and R over here, but it's the same thing. It's both the reliability value. So then we hit enter and we get a final answer of this comes out to, again, we call it P, we can call it R, 0.893. Final answer for the system. Any questions? Anything not clear or anything you'd like to explore further?
This part is clear. I in a system you mentioned earlier, if you had non-redundant generators, you could potentially have something like this where the generators are in series leading into it. In real world situations, what kind of scenarios would that be? Like, okay, you'll have two generators, but maybe one after the first generator, you'll have a split bus somewhere going somewhere else, or what's the point of having two series generators feed the downstream line? That's my question.
Sure. So electrically, they would still be considered, electrically, they're still connected in parallel, but if if say both of these are required to power the customer, so maybe generator number one can only supply 75% of the load. Generator number two supplies the remaining 25% of the total customer bus load. And the question asks for, total 100% reliable electric power for the customer bus. We're still wired in parallel, right, to this bus to send power. But in that case, since neither generator is large enough for the whole customer, in that case, we would have generator one in series with generator number two, along with the series transformers
Okay.
when we model our block diagram. Again, this block diagram just helps us add up all of the probability values to get the overall probability of the system. It's important, they're still wired in parallel. That's an electrical connection, but this block diagram that we're modeling doesn't really necessarily always have to do with how they're connected electrically. It has to deal with redundancy. And so now, for example, if I lose generator number two, right? Maybe I can still supply 75% of the customer load, but if the problem was asking for in order to supply the entire customer load, right? We lost that in this case. So that's
Yeah.
why we would model it in series in that case.
Okay, that makes sense. Yeah, that's what I was missing earlier. The physical connection versus the representation of the probability.
Great. And did that example help? Let's say if a generator is not big enough?
Yeah, yeah.
Yeah,
It helped.
normally, I mean, utility generators are pretty big. Were you in class last night for day two of protection?
Yes.
Do you remember that example we did on load shedding with the frequency relay where we had like a plant generator? It was very similar, but like the plant generator is not big enough to supply all of its own load, so it still imports a little bit from the utility.
Yeah.
That'd be like a really realistic real world example of that.
Okay.
All right. I just want to show you really quick before moving forward. So reference handbook has these formulas. All of these formulas for reliability block diagrams are on page 22 of the reference handbook. And it's no different than the way we did it. It's just the handbook kind of represents it slightly different. So again, reference handbook calls it P for probability instead of R for reliability. Same thing. And are you familiar with this notation, the capital letter pi?
That's multiplication.
Yep, capital pi. P stands for product. And math, product means we multiply. That's why they use Greek letter pi. And here it's just saying your overall probability of reliability for your system is going to equal you're multiplying by the total number of blocks. And this is for series blocks. So we got two series blocks, right? Transformer one, transformer two.
Hmm.
So we're starting at one, total number of blocks is two, and it's just saying, all right, pretty much saying when they're in series, you multiply their p values. That's all. Just like same value we got when we multiplied them, 0.9024. That was the equivalent of the two series transformers. And
Okay.
then on the parallel blocks, remember I just multiplied their two F values for the two generators that were in parallel. The reference handbook formula, it does the same thing, it just represents it a little bit differently. So here's the formula for how to combine parallel blocks. So remember, R plus F always equals 1. F equals, F equals 1 minus R. So this relationship, 1 minus the reliability of generator number 2, that's like the unreliability of generator 2. And then 1 minus the probability of reliability for generator number 1, that's the same thing as FG1. Remember when we multiplied the two unreliability values?
Yeah.
So when we multiply them together, we end up with FG1 in parallel with FG2. We still got to convert back to reliability. And how do we do that? Reliability equals 1 minus F. Reliability equals 1 minus F. It's the same thing.
Got it.
Make sense?
It does. Thank you.
You want to push on? Or you feel comfortable here?
Yeah, I feel yeah, let's move forward.
All right, let's do it. Next problem. So great time to talk about this, especially since we just got done with this last night. So 71, we've got a time current characteristic graph. We've got three different overcurrent devices. We've got one motor that's not shown. Problem asks for select the device setting change that will most likely result in proper selective coordination. So meaning we assume that right now the system is not properly coordinated. Can you see why the system is not properly coordinated?
It's because the A and the B are overlapping.
Perfect. Yeah, right here, this region right here. So if I look at the single line diagram, circuit breaker A is the most upstream. That's circuit breaker A in this like beige color. Circuit breaker B is right in the middle. Here's circuit breaker B in blue. And then the final kind of the branch circuit protection for the motor is fuse 1, which is in green. So if I had a fault that was, say, so our horizontal, we're dealing with current on a log scale. If I had, say, a 50 amp short circuit and maybe it was occurring right here. Actually, let's move this over. If I had a fault right in between here, but not at the level of the fuse, that's a better example. If I had a fault in between 10 and 50, right? And we would want just circuit breaker B to trip. Well, right now, circuit breaker A is going to start to unlatch first. And then we could also end up tripping circuit breaker B right around here if it's not fully cleared by A. So really all we're looking to do is how do we get this overlap? How do we get it so it's not overlapped? We want to get everything from A to the right and above of everything in blue from circuit breaker B. That way, if I've got this fault current right here, B is going to trip before A. Maybe that fault current is downstream of B, right? Here's our fault. And we want B to trip. We don't want A to trip because this is a single line diagram, right? But we're assuming this is a big bus. We're assuming we've got more breakers being fed from circuit breaker A to where if circuit breaker A trips, not only do we lose B, but we also lose any other breakers on this bus, right? So we only want circuit breaker B to trip for this fault right here. Make sense?
It does. Yes.
All right, so I'm looking at the time current curve. There's actually two different ways we could do this. One of the two ways are a correct answer choice. Do you remember from last night? There's two main changes we can make, right? What happens if I change the tap setting?
You'll move horizontally on the scale.
Yeah, tap setting has to deal with our amps. So that's a horizontal movement. First of all, I'm not worried anything about fuse one, right? This could not even be on the diagram and not affect this problem. So if I'm looking at the tap setting shifts kind of the horizontal portion of the scale. Now, have you ever had a chance to mess with these curves on like SKM or Easy Power or anything like that?
No, I haven't.
Okay. Um, if you've played with these curves, it's kind of more intuitive, but I'm gonna kind of describe the best way with a pen, kind of what happens when you shift them. So shifting the tap setting. Let's pick on circuit breaker A. First of all, we've got three different regions. There's circuit breaker A has a short time region and it has a long time region, anything above. Breaker B, this is an instantaneous region. That would be like our ANSI 50. And then this is another short time region. That would be ANSI 51. No different from this week's class. And then this would be long time. And then this period would also be long time, another ANSI 51 function. So you've got a couple of different segments of these curves, right? We can adjust the tap setting. We can adjust the time delay for the ANSI 51s. And we can also adjust the curve type, make them more or less inverse, but that's not part of this the answer choices. The key to realize is so when I adjust the tap setting, I'm only adjusting the tap setting of one portion of the curve. So for example, this would be the tap setting for the long time trip region for circuit breaker A. This value right here, that leading edge. So if I adjust the tap setting, if I can move this vertical portion to the right, I could potentially get it out of the overlap with blue. Does that make sense?
Yes.
So if I were to change this tap setting for the long time region for circuit breaker A, this is kind of what it looks like when you draw or when you adjust these on like SKM or Easy Power. I'm just tracing that rectangular portion. So if I can adjust the tap setting, I want to get it away from circuit breaker B and blue. Does this represent an increase or a decrease in the tap setting?
That's an increase.
That's an increase. Perfect. So notice how this portion of the curve doesn't change, right?
Mhm.
It's almost like that knee point, you know what I mean, kind of moves with the curve, this knee point right here. So if I can move it even right here where I've got just a little bit of overlap, it would no longer be miscoordinated. And
Yeah.
our new curve would look like this. Like even just a little bit of gap here would mean they'd no longer be kind of overlapping. But you notice here, you see that? Notice here's that new knee spot. We still have that inverse shape right here, right? We've just moved the longer vertical version to the right by increasing the tap setting. Does that make sense?
Yes.
Similarly, look, if we could decrease the tap setting, although that would just result in worse miscoordination. But again, just to help you visualize how these curves move. So I'm just tracing the vertical region. If we were to decrease the tap setting, make it more sensitive, maybe all the way over to here. And then I'm just gonna line this up right here. This would be the new the new curve for this guy right here. So we still have, again, notice how the knee point has shifted. It was right here for beige. Now it's all the way up here. Again, which would be even more miscoordinated because then look, all of this overlap right here.
Yeah.
So don't want to do that, right? Want to increase the tap setting. So that was one of the potential answers was to, or I think that was the potential answer, increase the tap setting for the long time trip region of circuit breaker A, right? All of this has all of this is gone, right? We've shifted the whole thing to the right.
Okay.
Let's look at the other answer choices and figure out, make sure we understand why they're incorrect. So like A is the answer. Increase the tap setting for the long time, essentially trip region for circuit breaker A. Notice, look, we could have would increasing the tap setting for the short time trip region of A have done anything, right? If I were to take this and shift that to the right, would that have helped anything in terms of my coordination?
No, we still
Not
have that
really.
overlap.
Yeah, we still have that overlap. Um, there's one other thing we could do. It's not a possible answer choice, but if it was, it would also be a correct answer. Like if this was a select the two correct answers, maybe this is like an AIT problem. Let's see if we can identify it. So again, here's the long time trip region. We talked about tap setting. What about time delay? What does time delay do?
It moves it on the vertical.
Perfect. So looking at circuit breaker A, if I were to increase the time delay or the time dial for this same long time trip region, here's what it would look like. I'm gonna use a different color besides blue because blue is too close to circuit breaker B. So I'm gonna use, I think orange is a better color. So this is what increasing the time delay would look like. Again, I'm tracing the curve, right? And just like you said, it would be an increase in the time delay is an increase on the vertical axis. So if I moved this up like that, here's what our new curve would look like. Does that get us out of the miscoordinated region? So that would be like shifting this whole thing up. And then look, again, this is gone, right? Here's our new curve. If this was filled in beige, again, we would no longer have any miscoordination. Does that make sense?
Yeah.
Not a
Here,
possible answer choice, but it is another viable way to fix the coordination. We could have either increased the tap setting, shifting the whole curve to the right, or we could have increased the time dial, increasing the curve vertically. Again, right and up away from circuit breaker B.
okay. So for coordination, you're essentially looking to make sure all your curves are clear of each other.
Yeah, exactly. There, you want them clear of each other. When you look at the single line diagram, you want the most upstream, you want the most upstream device to be furthest top and to the right. You want it all the way up in this corner. And the furthest downstream device, you want it to be down here. And you want there to be no overlap from your most upstream device to your most downstream device.
Yeah, that's a really helpful way to look at it.
Another thing we could have done, again, it's not a possible answer choice. It could have been though, right? is what about circuit breaker B? Could we have increased or instead maybe decreased any of its settings to get it out of this overlap region?
Yeah, you could decrease the tap setting,
Sure. Um,
but not by much because I see that fuse.
yeah, but it's close. We can try it. But so this time, so here's the short time region. Instead of messing with the long time region, which is up here, we'd have to mess with the short time AAA, right? If I decrease the tap setting of the long time, then I'm actually bringing no, it'd be I'm not sure. We'd probably still have some overlap before hitting that fuse. But look, what if we decrease the tap setting of the short time region in the middle? I think we might have a good shot. So here's the short time region. This leading edge, that's the tap setting for short time. Whatever the value is on the horizontal axis would be your tap setting, would be your secondary pickup setting for your ANSI 51 inverse time overcurrent relay, where this is like a moderate inverse or definite inverse curve. It's almost perfectly flat. So if I trace this, let's see if we can clear that overlap. So again, I'm just tracing the short time region that has to deal with the tap setting. Make these really big. We might just be able to make it. Let's see. There could still be just a little bit of overlap. All right. So I'm going to take this and I'm going to move along the horizontal. I don't think we're going to make it. Nope. Because as soon as we get here, look, we're going to overlap. We're going to overlap the fuse right here. And we're still miscoordinated right here with circuit breaker A. This would be the shape of our new circuit breaker B curve. Yeah, so not it wouldn't work in this case. We're still miscoordinated here, and we're out of room. We're only going to cause further miscoordination with the fuse. Yeah. Ibrahim, yep, I like it in the chat. That's exactly what we're going to try next. How about can we try then if tap setting for circuit breaker B isn't going to work by decreasing it? What about the time delay for circuit breaker B? What do we think?
Yeah, reduce it.
Yeah, reduce it. Which region, the short region or the long region?
Long region.
Long region. Let's try it. So again, to reduce the time delay, I'm tracing this portion of the curve. I'm just making it real big first. So here's one. It's pretty neat. If you ever get the chance to play with the software, it's I'm drawing the lines to show how they move, but a lot
Mhm.
of times you can just click and drag a portion of the curve and drag it up and down. It's a really neat visual. All right, so we're gonna leave no change to the long time tap setting. So I'm gonna mark the boundary. I'm marking the vertical boundary, and then all we're gonna do is we're going to decrease the time delay. So decreasing the time delay, I'm following this vertical curve with my mouse as just a guide. And we're gonna slowly bring it down. Aha, look at that. We have plenty of room here. Look, we can go right there. So now our redrawn curve would look like this with a decrease in time delay for the long time trip. Looks good. Yeah. So that would also be a correct answer choice if it was presented to us. And then look, so all of this blue area, we've shifted it down by decreasing the time delay, right? And then in the new shape, we no longer have miscoordination. So this would be the area of our new long time trip region for circuit breaker B in blue, which would also be perfect. Sounds
Makes
good?
sense. Yep.
I do want to look at some of the diagrams in the solution. They're really helpful, but before I do that, do you have any questions on the time current curve as shown in the problem?
No, no questions. I all my questions were just answered.
Excellent. That's what I like to hear. So a few of the other answer choices, enabling instantaneous trip for circuit breaker A. So currently, circuit breaker A in beige, it doesn't have the instantaneous trip turned on. You can tell because there's nothing here. Instantaneous trip is usually from 0 seconds to 0.05. So exactly where the blue region is. What would happen if we turned on the instantaneous trip, maybe say about here for circuit breaker A? Would that help or would it make even worse miscoordination?
Even worse.
Even worse, yeah. So
Yeah.
that can't be it. Um, Increase the short time delay for circuit breaker B, which would be the opposite of what we just did, right? It'd be like if we raised this up, not going to help, right? Raising it up, we still have some miscoordination. So that can't work. And then what else?
Well, that's the short time. That's the long time that we did.
That is.
The short time would be the bottom. Well, not the bottom, but right
It
here.
would. Yeah. So let's trace that out. Good eye. So here's the short time. And let's increase the timed. I'm not worried about this overlap right here. I'm just drawing it as a guide. Yeah. Let's increase the short time delay. We're still going to have some mismatch right here, right along this edge. Yeah.
Yeah. And then we still have the overlap.
Yeah. Still got some overlap. And I'll be honest. I'm not sure even if we could increase the short time that high because now we're way into the time delay of long time. So I'm not even sure if that would potentially be an option. We would only be able to increase it so much and
Yeah.
to still be within the short time region. But assuming even if we could raise it to the max, there's still going to be some overlap.
Mhm.
All right, so C, not an option, and then D, decrease the long time tap setting for circuit breaker A. Here's the long time tap setting for circuit breaker A. That would just what? Further cause even more miscoordination. So here's a good overview. Look, here's the instantaneous trip region. Again, it ends right here at about 0.05, right here. Short time trip is 0.05 to I think it goes up to zero point 0.5. Yeah, right here. Short time trip goes up to zero point 0.5. So that would have answered our earlier question of how high we could probably raise it. Um, so the lowest for short time is here, 0.5, where instantaneous ends, and then the highest would be zero point 0.5, right about here. So that's our short time region.
Are we expected to inherently just know these boundaries, or are you typically given?
It's hard to say. The way I always remember it, instantaneous typically has no intentional delay, right? Instantaneous is going to sit flat on the horizontal axis at 0 seconds. So if I'm looking at a diagram, I'm looking for that first rectangular shape sitting on the axis. I'm looking for like, where does it end? I know it ends along this boundary. So I know this has to be my short time. I know this is the pickup for your instantaneous. This is the pickup for your short time. This value is your pickup for your long time. So it's easy to see where short time starts. And then I know long time is kind of all up here. It's for me, it's hard to kind of remember these two, like where short time ends, where long time begins, because it's not as clear cut compared to instantaneous and short time. But in general, as long as you're good at recognizing that this is instantaneous, the pickup for long time is all the way up here. Pickup for short time is your next kind of bend in the knee. And then between short time and long time, it's going to be somewhere in between. You'll usually be okay. All right, let's see. No different than what you talked about. We can increase the tap setting by moving it to the right, decrease the tap setting by moving it to the left. We can increase time delay by shifting the whole curve up, decrease time delay by shifting the whole curve down. Nothing different. Here was the answer, increasing the long time tap. Again, the tap setting, same thing as your secondary pickup. Here's the new pickup, whatever that is on the horizontal axis, right? It's right where that leading edge starts. Previously, it was like somewhere over here. So increasing the tap setting, it's like dragging just that vertical portion of long time all the way to the right, specifically for the tap setting for long time. And then this shows enabling instantaneous trip for circuit breaker A would be here. You can see the miscoordination. Here's now we have an instantaneous region for A and the instantaneous region for B that was already there again. Lots of miscoordination here now. This was increasing the short time delay for setting. So this is what we tried, remember?
Yeah.
And yeah, your short time ends generally at zero point 0.5. So I put that, this is a log scale. So yeah. So yeah, we still have that massive area of miscoordination and a little bit of new miscoordination right here. And then decrease the long time tap setting. Again, here's the tap setting for long time, the new tap setting. The old tap setting was somewhere over here. And yeah, by decreasing it again, we're just getting even more overlap, even more miscoordination. All right, how you feeling? Feel good on the on this one on the time current curve?
Yes, absolutely. Very helpful.
Excellent. Yeah. It's really just it's like a puzzle. How do I get everything so there's no overlap? Overlap, miscoordination generally.
Yeah.
And miscoordination just means, I want the minimum number of breakers to open so that my outage is as small as possible. When there's miscoordination, you get more than one device opening and you got a much bigger widespread outage. All right, let's see. Five was about, yeah, difference between AFCIs, arc fault circuit interrupters, and ground fault circuit interrupters. Okay. So this was only on AFCIs, and in your email, you were curious about the difference between the two.
Yes. Just to get your take on it.
Yeah, sure. So a GFCI, generally it's either built into the receptacle. Anytime you see like the push, the test or reset, maybe, wife's trying to use a hair dryer, she's complaining it's not working, just got to hit the reset button. Or there's also GFCI breakers that you can use as well. The way these devices work, so here's our single pole breaker coming out of the panel, 120 volts. Here's our hot coming off the breaker. Here's our neutral return. And here's our receptacle. Something like this. So the way the GFCI works, whether or not it's built into the receptacle, or built into the breaker, it's the same thing. It's essentially a special, it's kind of like a coil around both wires. Um, think of it as a similar to a current transformer, right? Current transformer, the wires go through it. So it's kind of like a current transformer. Instead of one wire going through it, I've got two wires. I've got my hot and my neutral. In normal conditions, what's the relationship with the current on my hot conductor compared to the current on the neutral conductor for a single phase 120 volt circuit?
Same current going in and out.
Same current going in and out. So, what current is this little current sensor going to measure if I've got the same coming in as the same going out?
Zero.
Zero. Yeah, exactly. It's going to be 0 amps. Now, if I got a ground fault, say we got something's plugged into this. Maybe it's, I don't know, it's a blender whizzing around making a protein shake. Um, maybe this, something here we'll say it's a metal case, like a metal blender. And what if the internal wires comes into contact with the metal case? We're going to have a ground fault. And now what we didn't show, so this grounding, we do have actually a third conductor, right? We have a third ground conductor. So now I've got a ground fault. And now I've got current that's going to go through the wire, but it's going to come down this way. Here's my ground fault current. Do I have any neutral current left? If I have a ground fault, if it's coming back this way instead of on my neutral?
No, everything's just shunted to ground.
Beautiful. Yeah. Now we've got this is now like short circuit current, boom, feeding at our ground fault point and then coming back on the grounding conductor. Am I still going to have 0 amps on the GFCI current sensor?
No,
Nah.
no, you just no more differential of zero.
Exactly. And then that's when the GFCI will trip either the circuit breaker, if it's built into the circuit breaker, or it's going to trip. There's a switch inside the receptacle. Anytime you see like the test reset button on a receptacle, that's how you know it's a GFCI. If it's code compliant, a lot of times there has to be a sticker that says GFCI. But yeah, you can either buy a GFCI breaker which provides ground fault protection on the whole circuit. Because this, it doesn't matter how many receptacles I have, this sensor device is right up at the breaker. Or another common thing is you can buy one GFCI receptacle, and then every receptacle you wire off of that GFCI receptacle will still be protected by it. It acts as like the GFCI breaker, basically. It can still look at differential current for everything going out. Does that make sense on how a GFCI works?
Yes, it does.
The reason why this is helpful is circuit breakers, like this is like huge for residential safety, right? A circuit breaker should trip on overload if this blender is heating up or my vacuum trips one of our circuits all the time. If the vacuum slowly, if we're, really vacuuming the carpet, the motor's getting hot, motor's drawing more amps. As that overload increases, that should pop the breaker, or technically ground fault is still a short circuit. It should also trip the breaker, right? The reason why GFCIs are so helpful from a safety standpoint is sometimes on a residential circuit, your ground fault current might not be high enough for this breaker to trip. It might not really register that as a dangerous level of short circuit current. Your GFCI is super sensitive. As soon as it reads any current, right? When you current coming in, current going out, just like you said, the differential is 0. As soon as you have current going out, but not coming back in, and it no longer measures 0 amps, it's going to trip immediately. It could be a quarter of an amp, it could be half an amp. It's going to detect right away that, hey, we expect all of our current to come back on the neutral. It's not, but I still have current flowing into the circuit. We got a ground fault somewhere, trip right away. So it's going to help your breaker trip when sometimes your ground fault current, this might not be large enough to trip the instantaneous trip setting on your breaker. All right, so and back to safety, the reason why that's so important is I'm making a protein shake. It's five. I'm not a morning person, so if I'm up at 5 a.m., I'm tired, right? My brain's definitely not working. If this thing's whizzing away, blending my protein, and I don't have it protected by a GFCI, and there's a ground fault, and that ground fault's not big enough to trip the breaker, what happens when I reach and I grab and pick up the metal blender?
Is that
Get zapped. Now I'm the path of return. So again, that's why huge for residential safety. To compare that to all arc fault interrupters, they're much more of a modern thing. I think they started coming on like 10, 15 years ago. Let's grab our circuit and clean it up. All right. So same circuit, but now it's protected by an arc fault circuit interrupter. I'm not sure if they make, has anyone in the chat seen an AFCI receptacle? Are those new? I've only ever seen AFCIs built into the breaker. They do? Charles said they do. I haven't seen them. And yeah, Charles said, I think it was 2003, the first year that the NEC required them. So more than 10 years, right? We're going on 2 decades. Arc fault circuit interrupters, the difference is instead of looking at differential current coming in, going out, they detect arcing current. They detect little arcs. Um, how many times, Wayne, have you plugged something in and you see like a little spark?
a lot?
Yeah, all the time.
Yeah,
Or even sometimes when I'm flicking a light switch, I can hear a little crackle.
crackling and go halfway between.
Yeah, yeah. If you do that, you will probably trip it if you have an arc fault current interrupter. But yeah, that crackle is an arc. You're gonna have a little bit of arcing on normal everyday use at 120 volts. uh it's to be expected, right? When we plug something in, we're literally taking a metal thing and shoving it into the metal prongs of the receptacle, right? There's no, you know, when you get like 480 volt motors, there's like arc chutes built into the breakers and lugs and all that. 120, it's not really as dangerous. It's no big deal to just shove a metal thing into another metal thing. But there's always going to be a little bit of arcing. Um, so your arc fault current interrupter, it'll interrupt the circuit just like a ground fault circuit interrupter will, CI circuit interrupter. So it'll open the circuit, but it's looking for arcing. There's built in, it's not as straightforward to explain as a GFCI. I've dug into it several times. The best way I understand it is you've got current sensing and you've got voltage sensing. And there's some electronics in there that are also looking for really high frequency. So when you arc, when it zaps, a lot of times that little zap will be a really high frequency arc. So it compares changes in voltage, changes in current, and changes in frequency to detect what it deems a dangerous arc. So they shouldn't be so sensitive that it's going to trip when you flick a light switch, or if I unplug my vacuum while it's running, guaranteed there's going to be a little zap, little arc in that receptacle. Um, they shouldn't trip for safe levels of arcing. They're not supposed to. Big common complaint in the industry is that they do. Sometimes you get one, when you install it, and you just got to throw it out. It's way too sensitive. It trips all the time. But they're intended to just trip for dangerous levels of arcing to where uh, a fire hazard could exist. So anytime you have an arc, if I've got I'm trying to think if there's like a pillow on the floor and it's a really soft cotton pillow with little fibers, and if it's leaned up against the wall on my receptacle and that receptacle has an arc, that arc could potentially ignite the flammable materials of that pillow. Boom, now you got a house fire. Or a funny story, a couple weeks ago, I was dealing with a squirrel in my attic. If that squirrel chewed through some wires and one of the wires arced, right? If the squirrel caused a short and now you got a little bit of a spark, if I've got any flammable material in my attic, if there's like any wood chips, wood fibers, the insulation shouldn't be flammable. But again, that arc, it's like, you ever see those survival shows where they're like trying to hand make a fire?
Mhm.
It's to protect against that kind of event from starting a fire.
Gotcha. Okay.
So GFCI, personal safety from us being shocked, from us becoming the path to ground. AFCI, more so to prevent, still for safety, but to prevent fires caused from electrical arcing. So when we look at the potential answers, we've got A, arc fault circuit interrupters protect residential circuits by de-energizing the branch circuit when the difference between the hot and neutral current is greater than approximately zero. Is
That's
that
G.
an, what's that? Yeah, you
That's a
got it.
GFCI.
That's a GFCI all day. Not arc fault, that's GFCI. But if someone's not familiar with the two, it's easy to be like, well, I've heard of that before. Maybe that's what it is. B, protect residential circuits by de-energizing anytime a circuit conductor overloads. Nah,
No.
nah. This would be the thermal region of a thermal magnetic breaker is what's designed for overloads. Like if you look at a thermal magnet breaker, it's very similar to circuit breaker B, where your thermal region is really your long time region that we're only looking at a smaller number of amps compared to like instantaneous for fault current. But you got a long, look, 400 seconds, right? That's an overload. So definitely not AFCI. C, AFCI protects by de-energizing the branch circuit when any amount of arcing is detected. And if we compare that to D, de-energizing the branch circuit when a dangerous level of arcing is detected.
Yeah. So that's D is the answer then, because
Bingo,
N means like if you're unplugging something like your vacuum, like you said,
bingo, bingo.
AFCI would show. Okay.
If I was taking the P exam tomorrow and if I had a problem like this and it just talked about de-energizing due to arcing, but there weren't two similar questions where one is saying any arcing, the other is saying dangerous levels. If I just have one choice that talked about interrupting due to arcing, I would pick it. But here it's a little bit of a trap because they're not designed to trip for any amount of arcing because that's part of using 120 electricity. There's always going to be some level of arcing, but it's so tiny that it's not really going to hurt anything, right? Arcing at higher voltage levels, way different story. That's why we have things like arc chutes and circuit breakers. That's why we use heavy duty motor contactors controlled by, lower voltages and et cetera. But 120, you're going to have some arcing in the box. It's just common. All right, questions on this? Let's see. We might have time to knock out that last problem. What you think?
Yeah. Yeah. No
Good.
questions here.
All right,
Let's
we're just a little bit over an hour, but let's go ahead. We'll knock out this last one for you, and then we'll have answered everything that you were concerned with. All right, so this problem comes straight from class 3 transformers. There's a lot more similar examples if you want to try them after this in the transformer connections module and the online review course. But you had talked about looking for an example where pretty much when we're dealing with a delta Y or Y delta transformer and the difference between maybe the single phase ratios and the three phase ratios. Is that right?
Yep.
All right, let's try it. So Problem says we've got three 1 to 10 or A equals 1 single phase transformers are connected Y delta. Um, Question. What part of the industry do you work in again?
Power electronics.
Power
So
electronics. Okay.
yeah, it's
Do,
not big power, but tiny power.
it's okay. What do you work on the design side, on the sales side, manufacturer side?
Mostly sales side right now,
Okay.
engineering, sales.
A lot of like UPSs and soft starters.
Yeah, power supplies, and, switch mode power supplies, UPSs,
Okay,
batteries.
great. Have you ever been on a job site and seen a really big transformer, or maybe driving down the road, you see a real big transformer,
Yes.
big tank?
Yep.
So a three-phase transformer, all it is, you've got three individual single-phase transformers that are inside that tank. And then we can either delta or Y connect them on the primary or secondary to make our three-phase transformer. But if you ever get the chance to look inside a tank of a transformer, usually they're sealed, right? You're energized, you can't. Um, but it's just you got three massive pairs of windings, and they're single phase transformers. It's just three single phase transformers in that tank. That's all it is. So this problem gives us the ratio of these single phase transformers that make up our three phase transformer. the the three individual single phase transformers, they're Y connected on the primary and they're delta connected on the secondary, making a three phase Y delta transformer. Problem says calculate the three phase voltage ratio if the primary line voltage is 2400 volts, common medium voltage. So first thing we do is we sketch out, all right, I've got a Y delta transformer. So I'm just going to draw a Y delta transformer. Let's see, the primary line voltage is 2400 volts. So I'm going to say from capital A to B, we've got 2400 volts magnitude, right? From here to here. Just looking at, we got that from B to C and C back to A, but we're just going to show it from A to B. So we want to know what's the three phase voltage ratio. What's V primary three phase to V secondary three phase? When we look at this Y and delta transformer. So this 1 to 10, that's like N1 to N2, not of this three phase transformer, but that's the single phase ratio of the individual transformers kind of inside the transformer tank. So we can visualize that. Look, I'm going to draw a winding from A to B. So here's the primary winding for one of the single phase transformers from capital A to capital B. And then that's the secondary winding would be from lowercase a to lowercase b on the delta side. So together, this makes one of the single phase transformers inside the overall three phase transformer. Does that make sense?
Yeah. But would it be? It wouldn't be B there, would it? On the left side, wouldn't it be N?
Oh, I'm sorry. Yes, thank you. You got it. Great eye. Capital neutral. Perfect. Because it's Y connected. So the ratio that they gave us in the problem, that's the ratio of this winding to this winding. I have two other single phase transformers, right? We looked at A to neutral. We also have B to neutral on the primary, and then B to C on the secondary. And then we have C to neutral on the primary. And then we have a third transformer would be from C to A. And each of those single phase transformer pairs have a ratio of 1 to 10. So the key here is realizing, look, since I'm Y connected on the primary side, Notice how we don't have the full line voltage applied to the primary winding, right? Since it's Y connected, we've got sorry if you can hear my dogs up here right now. Since it's Y connected, we've got the line to neutral voltage or the phase voltage of the Y connected. That's what's applied directly on this primary winding. And that's where we're going to have a sneaky square root of 3 pop up in here. So down here, this diagram is a single phase transformer. And we're looking at the single phase transformer here in this red box from capital A to capital neutral on the primary, like you caught, and then from lowercase a to lowercase b on the secondary. So this transformer is just one of the individual single phase transformers out of the three total that make up this three phase Y delta, or yeah, Y delta transformer. Does that make sense?
Yes, it does.
Great. How do we figure out the voltage applied directly across the primary winding from capital A to capital neutral of this single phase transformer?
That's gonna be the 2400 divided by root 3.
Yeah, you got it. We're going from line voltage A to B, right? From here to the phase voltage from A to neutral. So just like you said, we're going to take our line voltage, 2400 volts, and we're going to divide it by square root of 3. Now, um, give me an angle. What's the easiest angle you can think of?
0.
0. Let's step this through the transformer. What's the ratio of the single phase transformer?
1 to 10.
1 to 10. Typically, when you're working with a three phase transformer, you don't really care about the single phase ratio unless you're studying for the P exam and they test you on it, right? In real life, three phase transformer, I just want to know what my three phase voltage ratio is. I want to know if I give 2400 volts across the line here, how much am I going to have across the line here? So that's what this problem is asking us to solve for. Very rarely do you encounter this in real life, but it's a common PE question. And it is helpful to know that, yes, depending on how your single phase transformers are connected, it can change the overall ratio. So let's step this across. Are we stepping the voltage up or are we stepping the voltage down?
Up.
Up. How do we know?
The going from 1 to 10.
Yeah, more number of turns. Remember, these aren't voltages, these are the ratio of the number of turns. More turns on the secondary side means more voltage on the secondary side. So now we're looking at the voltage from lowercase a to b. I'm going to start with just the magnitude. If we're stepping the magnitude up, where does the bigger number go in the ratio?
Up.
Yeah, it goes on top. So I've got 10 to 1. Now, when I step across a single phase transformer, does the angle change at all? Can it have any change on the angle?
No, stays the
No,
same.
no. Uh, we're just stepping up or stepping down the magnitude, right? Only when we're talking about a single phase transformer. All right, what do we get for the voltage from A to B? Let's see. 2400 divided by the square root of 3, and we're stepping it up by a factor of 10. So we get a little more than 13.8 kV, right? We get 13,800. I'm just going to round to the nearest whole volt, 856 volts. Again, no change to the angle. That's the voltage from A to B. Now, how do I calculate, trick question, of course, how do I calculate the secondary line voltage from this voltage?
It's the same.
Yeah, it's
Delta.
the same. Tell me, why is it the same?
That delta V line is equal to the V phase.
Beautiful. Yeah, it's delta connected. So the voltage from here to here equals the voltage from here to here. Essentially, it's in parallel. So we've got our secondary line voltage magnitude and angle. We've got our primary line voltage magnitude. We already kind of figured out the three-phase voltage ratio, but let's just talk about the phase shift as well. Earlier, I asked you to pick an angle. I said pick the easiest angle you can think of for A to neutral, right, on the Y side, and you
Mhm.
said 0 degrees. If the Y line to neutral phase voltage from A to neutral is 0 degrees, what's the angle of the Y primary line voltage from A to B?
That's 30 degrees,
Perfect. Assuming what?
assuming you started off with zero.
We'll say assuming balance and positive
Balance
sequence.
point. Okay. Yeah.
So I don't think this problem says that. But yes, absolutely correct. So first, problem asks for what's the three-phase voltage ratio? Let's figure that out, and then we'll talk about this interesting phase shift. Here's a kind of like a wiring diagram for a three-phase transformer. Here's just the single line diagram. So this single line diagram, if I apply 2400 volts primary, I'm gonna get about 13.8 kV. How about we'll make that a slash so it doesn't look like we're dividing. So notice that this is a little different than the 1 to 10 ratio of the single phase transformer compared to the three-phase transformer, right? Uh, 2400 times 10 is not 13.8 kV. So here's what we typically call this the hidden square root of 3, right? Right here. We had to include a square root of 3 because we're using our single phase turns ratio and our transformers connected Y delta, which means the voltage applied across the primary winding on our Y side, it's not the line voltage, it's the line to neutral voltage. So we had to divide the line voltage by the square root of 3 to figure out, okay, what's the voltage actually applied on the primary of the transformer? What's the voltage that actually gets stepped up according to the single phase voltage ratio? Does that make sense?
Yes, it does.
So we could even think of, look, what is the three phase ratio? We'll compare it to zero point 0.1, right? 1 divided by 10 was zero point 0.1 single phase.
Mhm.
The three-phase voltage ratio, 2400 over 13.8 actually works out to be 1.73. That's square root of 3. That works out well. Um, yeah, notice it's different. This is the three-phase voltage ratio. This is the three-phase turns ratio. This is the single phase turns ratio. And then we could figure out if we want to find out the single phase voltage ratio of each transformer to compare, it would be 2400 divided by the square root of 3 compared to times 10, right? We would have 1,387 to 10 times that amount. Again, looking at just the single phase voltage ratio of the three-phase transformer, it does not equal the three-phase voltage ratio of the three-phase transformer. It's all because of the Y delta connection. We got a hidden square root of 3 here.
Makes sense.
That makes sense? Typically, we don't even have to worry about this, right? Typically, they're going to give us the three-phase voltage ratio. Using this voltage ratio, if I apply 2400 volts primary, what's my secondary line voltage going to be?
13.585. Okay.
Yeah, 13,856. When you're given your three-phase voltage ratio, any hidden square root of threes, they're automatically baked into that number. They're automatically included. You don't have to worry about them.
Okay. Makes sense.
If it's a three-phase transform, if I'm working in the field, I don't really care about the single phase turns ratio. It's a three-phase transformer. I'm giving it three-phase voltage. I want to know if I give it this much, how much am I going to have on the other side, regardless of how the transformer is connected. Just tell me how much voltage I'm going to have on the secondary side. That's all I care about. So you're really only going to see this if you're asked about it on the PE exam. And at most, I mean, I can't expect you to see more than one or two of these problems. But uh, these hidden square root of threes and the phase shift, it only happens if you've got y delta or delta y.
Okay. So if
And
you
then
have a y, then it's just straightforward or a delta delta.
it a y you divide by the square root of three on the primary side. And then once you step through the transformer, you multiply by the square root of three on the secondary side. So it cancels out. And then last thing we'll talk about is the phase shift. Look at this. So on the single phase level, was there any phase shift? 0 degrees, 0 degrees?
No.
No. What do you notice about the three phase line voltage level? 30
Yeah.
degrees, 0 degrees.
Mm,
Again, you got a phase shift for the same reason you got the hidden square root of three. We're going from line VAB plus minus to phase A to neutral. A to neutral. Two things, right? We divide by the square root of three and we lag by 30 to go from line to phase. 30 minus 30 gives us our zero.
yeah, that's
Makes sense.
straightforward.
Good practice if you want to try it. So
Mhm.
this comes straight from class three transformers, is to try this out, same problem, but make it a delta Y transformer instead. And if you're curious, post it on the student message board and we can take a look at it together. You'll still have a hidden square root of three. You'll still have a phase shift, but now the Y is going to be on the secondary side. So it's going to happen after you step through the transformer instead of before.
Okay.
Cool. Any questions?
No, I think I'm tapped out. Um,
Good.
yeah, definitely straightforward. This is very helpful. It clarified everything that I came in looking to get clarification on.
Great. That's always my goal. I mean, we went about 20 minutes over. No big deal for me. I didn't have anything else scheduled for after this one, so happy to do it. Hey, keep up all the hard work. You said April 22nd.
Yes, sir.
Man, keep up all the hard work. Keep doing what you're doing. Keep those 8 hour really fun study sessions. Keep at them. Post questions on the student message board when you have them. Keep that index. Keep coming back to the index every few weeks. Try to really use repetition for any problems that are just giving you a hard time.
Okay. Well, thank you, Zach. I really appreciate this. And good luck to everyone else that's watching.
Awesome. Yeah. Hey, my pleasure. I enjoyed it. Great meeting you face to face as well. If you have any questions at all in the future, you know where to find me.
Yes, thank you. Have a good day.
See you, Wayne. You too.